Hi, this is Claire, and I'm going to talk to you about applying Pythagoras to 3 dimensions. The first thing we're going to draw is an ellipse, and if you have your grid paper and a ruler, I've actually got a set square this time. So draw a 6 centimetre line, and then on each side, look at going out 3 squares and up 4 and put a dot. So across 3 and up 4 and construct a parallel line that is exactly 6 centimetres long. Join the ends, and what you're actually constructing here is a parallelogram, but it's going to serve as the grid or the actual construction lines for an ellipse. And I'm just going to make it a little bit lighter so that it's not too dark, because that's pretty dark. I did draw that a little bit too dark. So that's actually giving me the construction lines for an ellipse. Now you can see there's 2 wide corners. So there's 2 corners that are a little bit wide, and there's 2 corners that are a bit more narrow. So these corners are obtuse, and these corners are acute. From about the midpoint of both of the lines sides, let's draw the large ellipse. So you draw a circle there and a circle on this side. Then on the narrow corners, you draw a smaller circle. So a little bit narrower here and a little bit narrower on the other side. So now we have an ellipse for the base. Find the centre of the ellipse by joining the corners or the diagonals of the original square. Well, it's actually a parallelogram. And when you find the centre, draw a perpendicular line, and let's make this 5 centimetres high. So I'm going to make sure I go exactly through the centre. So I'll just keep that light because it's a construction line. And we're going to draw a cone. Taking your ruler, from the apex, draw a line which just touches the curve, the outside curve of the original ellipse. We call that a tangent because it's just brushing that curve. Do that on both sides and you have constructed a cone. Now it's a sort of a transparent cone because you can see inside. Now we know that the height of that cone is 5 centimetres. And that height line forms a right angle with the base. So you can draw a triangle anywhere in there, anywhere you like, and it meets the height line at a 90-degree angle. So what you end up with is a right angle triangle. Because I'm working to scale and I know that that was 6 centimetres long, the radius of the circle is 3 centimetres. So we can calculate the slant length of the cone. So that is called S, or slant length, and that's a symbol that's always used for the slant length of a cone. So using your Pythagoras theorem, S is actually the same as the hypotenuse. So to be S squared equals 5 squared plus 3 squared, which equals 25 plus 9. And if you add those together, you will get 34. So S squared is 34. S will be the square root of 34. So we'll need to use our calculator for that. So getting your calculator and turning it on. So square root of 34 is 5.83. Rounded to 1 decimal place will just be 5.8. So S is 5.8 centimetres. So that's the length of the slant of this cone. So if you wanted to draw a cylinder, you would do this in a similar fashion. So let's make our cylinder 5. We'll draw a square to fit it in. So drawing a simple parallelogram with the front length 5 and I've gone back 3 and up 4, so back 3 and up 4, and that just ensures on the grid paper that I have some parallel lines. And I have drawn a rectangle that I can construct an ellipse in. Unfortunately, Cleo is feeling like having a bit of a bark at the moment, so I'm sorry about that. There's obviously something going on that she can hear that I can't hear. So once you've constructed that ellipse, you can decide on the height that you'd like to make it. Let's make this cylinder 4 centimetres high. So take each corner up 4 centimetres and construct the top of this. So I'm just keeping as accurate as I can and working as quickly as I can. So construct the top of it. Now you're actually using a rectangular or a cube type cuboid shape to fit the cylinder in above here. And the same way, wide circles where the corners are wide, smaller, narrower circles where the corners are acute, and then drawing vertical lines between the two as accurately as you can. There's one. This one didn't look quite as accurate, but you can see there is a cylinder shape. Now you might be asked to find the longest pole that could fit inside this cylinder. Just say it's a tank. It's not going to be a vertical pole, because the vertical pole will only be 4 centimetres or 4 metres. It will be the diagonal from the base up to the top. That is the longest pole that will fit inside a cylinder, and it forms a triangle with the right angle on the side. So once you've constructed that triangle, you can use Pythagoras. Now the base was 5 metres, the height was 4, and we need to calculate the diagonal here. Let's call it D. So it will be D squared equals 4 squared plus 5 squared, which will equal 16 plus 25. So 16 plus 25 is 49. So you've got 11. It's not 49. Sorry about that. Am I saying about... You've got 6 and 5 is 11. Carry the 1. And you've got 30 and 40. 41, not 49, sorry. And if you want to find D here, you find the square root of 41. We'll need to use our calculator for that. So clear, square root 41, find the square root of that, it's 6.4. So 6.4 is the longest, 6.4 metres, or is the longest pole that would fit inside that cylinder. So as you can see, you can construct a lot of shapes on grid paper. If you want to draw a rectangular solid, it's much the same as you would draw this square here. So simply start with a parallelogram base, and I'll just move this a bit closer so you can see it. If we wanted to make it 4 centimetres, draw your 4 centimetres, then maybe go back 3, up 4, go back 3, up 4, put another dot, construct the other line and join the corners. So you have that. Then decide on how high, and just use a perpendicular line to draw each corner. So you might decide to make that perhaps 3 centimetres high. So construct a perpendicular line from each corner, 3 centimetres high, right up here. And you're constructing a rectangular solid or a cuboid. And you will need to be able to do this to do the problem solving exercise that I have put on OneNote for you to complete. So label all the dimensions of this. So this one, if we make 1 centimetre represent a metre, that would be 4 metres. And up here, this is going to be 3 metres. And this we'll say is not a square, it's actually 2.5 metres here depth. The depth is 2.5 metres. So that's length, width and height, and that's the way it's always expressed. Length times width times height. Okay, so that's a little bit of information about using Pythagoras in 3 dimensions, and that relates to the work we're going to do today. So I'll sign off now and thank you for your attention. Bye.